Hi Chargers, today we're going to talk about section 10.2, simplifying radical expressions. Let's jump right in. A radical expression contains a radical, so we'll go ahead and put that in, contains a radical, which is, as we know it, this little square rooty dude. And that's pretty much the only requirement. It has to contain a radical. For all intents and purposes, for this class, we're going to be using the square root. If we want to simplify it, oh, one more thing. We've spoken about before, if you have the square root of x, the checkmarky looking thing on the outside is called the radical, like your super radical, and the x, just to remind you, is called the radicand. Okay, radical, radicand. A radicand in the simplest form if the following conditions are true. No radicands have perfect square factors other than 1. That pretty much means you can't divide your radicand by a perfect square that's more than 1. No radicands, for number 2 here, contain fractions. So it cannot be, not what I just wrote, don't write that. It cannot be the square root of 3/5. Can't be that. Last but not least, no radicals appear in the denominator. Well, that's not how you spell the. Denominator of a fraction. So we can't have 4 over the square root of 7. Okay? Those 3 conditions. No radicands have perfect square factors other than 1. No radicands contain fractions. And no radicals appear in the denominator of a fraction. So let's go here to what the product property of square root says. That says if we have a square root of a, for instance, and a b also underneath there, that we can split this up into the square root of a times the square root of b. And that's also the reverse is the same. If you've got the square root of a number times the square root of another number, you can rewrite it as the square root of those 2 numbers multiplied together. All right, it's going to be important for what we do next, which is simplify radicals. So it's important to know here what our prime factors are. So we're going to take 80. I need 2 numbers I can multiply together to get 80. Let's do 4 and 20. Yes, that's a 4. Quit your silent judging. So I want to break 4 down into all the numbers that multiply together to get 4. So that's 2 and 2. 20, I can make 5 and 4. 2, I can't do anything else with, but I'm just going to bring them down anyways. 5 is a prime. 4, I can make 2 and 2. So here's what we're going to do. The bottom row is all prime numbers. If they're pairs, I'm going to make a little v, and I'm going to write what that number is. So we have a pair of 2s, so we're going to have 2 here. There's also a pair of 2s, we're going to have 2 there. Anything not in a pair, I'm going to circle. So let's simplify. I'm going to go ahead and make a radical. Anything that is underneath a v is going to go outside. So 2 times 2 is going to go outside of my radical. Anything circled is going to go inside. 5. So just to simplify one little baby step further, 2 times 2 is 4, and square root of 5 is that. So I know you're asking yourself, how can I check and see if this is correct? Well, I'm going to show you. We're going to take 4 and square it and multiply that by 5. So 4 squared is 16, and 16 times 5 is definitely 80. So whatever this is, and this number should take us back to our original radicand. Okay? Let's try another one where we can use that product property of square roots. We've got the square root of 2 times the square root of 14. I need to multiply those together to simplify. But I'm not going to multiply them. It sounds, I'm thinking I sound crazy, and I probably do. But I'm going to have to split them up into prime factors anyways. So before I do that, I'm just going to factor them now. 2 is prime. 14 is 7 times 2. Well, I've got a pair of 2's and a 7 that's not a pair of anything. So to rewrite it in a factored simplified form, I write 2 times the square root of 7. The 2 is underneath a pair. The 7 is circled and goes in the radicand. All right, let's move on. Example 3. Now I'm going to add in some really exciting variables. These are going to work the same way. I'm going to write x's. How many are there? There's 3 x's. There's 4 y's and 5 z's. Now I'm going to do 90. Let's simplify that. Let's do 9 times 10. 9 is 3 and 3. 10 is 5 and 2. Those are all primes. I've got a pair of 3's and 5 and 2. I'm going to multiply those together when I put them back under the radical. Let's do the same thing for our variables. I've got a pair of x's, and then 1 single solitary x, a pair of y's, and another pair of y's. None remaining, by the way. A pair of z's, another pair of z's, and then 1 little baby z all by itself. So like I said, anything that goes out in front of the radical is going to be multiplied together. So I've got a 3 that goes out front, 1x, 2 y's, and 2 z's. So 3xy squared, z squared. 3x, y squared, z squared. Underneath the radicand is going to be everything that's circled. 5 times 2 is 10, and there's an x and a z. And that's our answer. It's as simplified as it can be. I hope that makes pretty good sense to you. If not, we will be working on it a lot, so not to despair. Okay, quotient property of square roots. That says that if I have a square root of a number over another number, I can split that up into the square root of one of those over the square root of the other one. And just like with the product property, the opposite is also the same. If you have 2 square roots, 2 radicals in a fraction, and you need to simplify, and you could simplify this fraction, this a times b, or a divided by b, you could put it into 1 single solitary fraction like this and simplify. All right, this says you can use the properties of square roots to rationalize the denominator. That means we get rid of the radical. This involves multiplying the numerator and the denominator by a factor that eliminates radicals in the denominator. Let's go ahead and show you what I mean. Let's split up. Let's simplify this fraction. We've got 35 over 15. We can divide them both by 5. So divide by 5, that's a division symbol. 35 divided by 5 is 7. 15 divided by 5 is 3. So now we have the square root of 7/3, which the quotient property tells us we can rewrite the square root of 7 over the square root of 3. And if I want to rationalize the denominator, I'm going to take whatever the bottom radical is, the square root of 3, and multiply that by the top and the bottom. And you'll see why in just a second. 7 times 3 is 21. 3, square root of 3 times the square root of 3 is the square root of 9. Well, I can't simplify square root of 21. 7 and 3 are both prime, so it's just going to stay the square root of 21. The square root of 9 is 3 times 3, which is a pair of 3s, which is what's going to go underneath my radical. Okay, clear so far? Let's do another one. We want to simplify the square root of 6y over the square root of 12. Let's do just like we did a moment ago. Let's put these in one radical, so 6y over 12, and then I can reduce the fraction. So I can divide those both by 2, and I get the square root of 3y over 6. Now I can divide them both by 3, and I get the square root of y over 2. Now I can split that back up into two radicals, the square root of y over the square root of 2. And just like before, I'm going to multiply the top and the bottom by the radical in the denominator. The top is going to become the square root of 2y, which I can't simplify. 2 and y are both primes. And the square root of 2 times the square root of 2 is the square root of 4. Well, that's a perfect square. And I can rewrite this, the square root of 2y over 2. And that's our answer. Now, you might be asking yourself, why is it that you can't take 2 over 2 and reduce? Well, it's because the square root of 2 is not the same thing as 2, okay? Not even close. We're going to save the rest for tomorrow. So please practice these two concepts, the quotient rule and the quotient property and the product property. And let's see what we can get done with that. Good luck. Let me know if you have any questions.